Folks, welcome to my class, Decision Modeling, and in this class we will be looking at how a manager basically makes a decision. Before that, my name is Zubair Muhammad. I'm the Professor and Chair of Management, and as I said, so this class is going to be interesting, and you can get as much out of this class, as much effort as you put in. And it's a very interesting class, and then you see that the application of the tools and techniques that we are going to go over in this class is applicable in your daily life, and you come across some examples not knowing that these are the models that are at work in your daily life, and I will mention those when I basically get into the topics and then how it affects you on a daily basis. Okay, but nonetheless, this is a very important class, and as businesses seek to be more competitive, so the cost side of the equation is what they can control. Many a times the revenue function could be out of their control because of the markets that are global and dynamic in nature, but what is under their control is their cost side of the equation. Okay, in other words, modeling the situation that they get in for better control becomes quite essential. Now, in this class, what we'll do is we will attempt to help managers what tools and techniques that there are available at their disposal to help them make good decisions. And of course, in any decision making, two important things that one should consider is the qualitative aspects that one needs to consider in decision making, as well as the quantitative factors. Okay, and here the focus is on the quantitative factors in this class. Okay, now there are certain things that one need to keep in mind when we talk about decision making, and of course, there is this method. What we are going to be talking about or involved in throughout the semester is based on scientific methods. Okay, and there is a good body of knowledge that has been generated in this field over the last 50-60 years, and there are a lot of professional societies also that are engaged in this, and there are hundreds of professionals across this country and across the globe that they are engaged in, and they hold annual meetings nationally, internationally, and their aim is to advance the body of knowledge in this area. Okay, so as I said before, here our focus is going to be on the quantitative side, and what we want to do is many a times our human mind has limitations and our approach can be myopic. Human mind, although it's complex but can help in good decision making, pretty soon, if you have a choice between two things, decision making becomes a lot more clearer. But if you have a choice between 10 different things and with 10 different impositions, etc., then the selection or decision making becomes difficult. So we have to at that time turn towards are there any scientific models that are there that can help us make those decisions. And while I go through this PowerPoint slides, you will see that I'm going to elaborate on some, then I'm going to skip on some. Okay, and at your convenience you can go over those, and of course I will also upload these PowerPoint slides on the Blackboard, so you'll have the lecture and also the slides on the Blackboard. Okay, now in this decision making, as I said, it's a rational way of arriving at a decision. There are certain steps that are involved in this process, and many a times, and of course you follow them through sequentially. It doesn't mean that you go through steps 1 through 6 in that order. At the end you have a decision making capability. It may not be. As and when you go through that, you would learn that something perhaps was missing, and it might take you back again to step 1 or step 2 or step 3, and likewise you may go through all 6 steps and see that the recommendation that you have is not going to address, so perhaps you missed out on some of the things in the earlier stage, so it will again take you back. So it's an iterative process until you feel that you have a decision for a problem or scenario that you are actually confronting. What are the 6 steps? The first one is to define the problem and gather the data. Actually problem or identification itself is half of the solution. If you don't have the problem identified correctly, then any solution that you basically propose is not going to address the problem that is there volitionally. Why? Because you misread or misrepresented the problem. So that is why in any decision making, more than half of the time is spent in identifying the problem correctly. Okay. Once you identify the problem correctly and the factors that need to be considered and gather data on those, then you are in a position to formulate a model. And typically, we represent those models in a mathematical fashion here. Of course, there are other ways of model representation that are available. You might have seen, that you might have built some models before, using Kinex or Lego or maybe sticks and other things like a bridge, and then you hang a weight on that and see when it snaps. So of course that's a good representation. That's a physical representation of a model. That is very important, because the scientists, they represent a physical representation of an entity, then subject that to the forces that occur in the nature, and that really helps them kind of go and redesign before they actually build a skyscraper, for example. But in our case, we are going to be using only the mathematical representation to solve those problems. Okay, and once we have those things, then we need to having a problem defined in a mathematical way is not enough, but we got to have a way to solve those things. So here in this course, we are going to be using the Excel as the base to solve those. And let me tell you one thing: this class is not about teaching you Excel. This class is about using Excel to address some problems that a manager faces in their daily life, be it is operational or tactical or strategic decision making. Okay, once we have the model and once we have the data, what we want to do is we want to input the data into the model and use Excel software. Okay, and run the software and test the model and refine as it is, it as needed. Then apply the model to analyze the problem and develop recommendations for management. Okay, now here, as I said, it could be an iterative process. You go back and forth, and when a time comes that you have a solution to a model, then you go to the step 6. There it is the implementation, and of course after implementation is the follow-up. As I said before, some of these slides I'm just going to skip forward to save on the time. Okay, now these are the important things that you need to consider. What we are trying to do is we are trying to represent a real life situation in mathematical terms, or we are going to capture the real life situation as a model. Real life is complex, extremely complex, and there may not be sophisticated mathematical tools available to capture the complexity. Even assuming that it's available, perhaps we may not have the solution procedures to solve those. Okay, so as a manager, what you do is you begin to make some assumptions, and assumptions basically simplifies the situation, and formulating a model becomes more practical and feasible. Okay, then you identify the decision variables. So these are the decisions that you are interested in. Those are the variables. Like for example, how much quantity do I need to produce? Okay, so that's a decision variable. Okay, if you want to maintain a certain ratio between, let's say, different types of products that are complementary in nature, okay, what is that ratio going to be? Okay, so that again is a decision variable. Then always there is an objective function. I mean, in the business world, many a times the objective is to maximize the bottom line, which is a profit. Okay, many a times when we do come across situations in which the objective could be to minimize the time to travel from place X to place Y, or minimize the project time, if you are involved with the project management, so there are certain situations. And of course constraints. Constraints are those things that are kind of imposing, meaning that Okay, I want to maximize my profit, so I want to produce my components. But of course, when you produce the components, you need labor and you need the resources such as material, capital, and all those things. They are not available infinite. So you cannot produce infinite quantity. So you have to produce only a certain number. Okay, so those are the ones that are constraints, like for example, availability of resources, availability of capital, how much of it is available. So so those are the constraints. So these are the restrictions, impositions that are there. Okay. Then parameters and technical coefficients, what they are is, like for example, if I am in the business of producing or assembling a computer, for example, each computer might take me about 20 minutes to assemble. So that's a technical coefficient or a parameter, is each unit consumes so much of a particular resource. So this is a typical representation. Here it is maximize my profit, and profit, this is a function, like for example 4x1 plus 5x2, meaning that each x1 gets you $4 in profit and each unit of x2 gets you $5 in profit. So that is that function. And or it could be minimize the project completion time. So here is a typical constraints that they were talking about in the previous slides. The first one is an equality constraint, that you see the equal sign, meaning that for example certain function that represents, say for example the machine capacity available, okay, that is consumed, that's on the left hand side, is equal to C1. C1 could be, we have 480 hours of machine time available, so that could be C1. The next function is a less than or equal to, that's an inequality. Okay, C2. Let's say that we have $100,000 to invest, and that function represents different portfolios where you could invest those monies. So what that says is the total amount that's available for investment or that we invest has to be less than or equal to C2, which is the capital, that's $100,000 available for investment. And a similar representation for C3. For example, let's say that we are talking about a for example, so in a diet, the protein amount should at least be equal to or greater than C3, maybe 10 units. And there are different ways of getting protein into your diet: meat, egg, poultry, and other things. So that is the function G3. So this is a typical representation of a complete model. So what we will do here is, we will do our best not to kind of go and, I do recognize the different backgrounds, that you people come from. Okay, and so what you see right there on the screen is called an algebraic representation, because that's nothing but algebra what you see in front of you. Okay, I will try my best not to kind of get into more details of this, but rather than straight away take a problem situation and develop a spreadsheet model. Okay, and I will elaborate on that when I get to that later on in perhaps next lecture. This is a typical representation. That's called a linear programming. Here you have a maximize 5x1 plus 7x2 plus 15x3. x1, x2, x3 are different products, and 5, 7, 15 are the unit profits. Okay, and here the first constraint says the amount that you produce of x1 and x2 together should be exactly equal to 100. This could be a number of tables plus number of chairs should equal 100, for example. Okay, and likewise the other two constraints could talk about the amount of assembly time that's available, or the amount of, let's say, the labor time available. Okay, that could be the last one, x1 greater than or equal to 0, x2 greater than or equal to 0, x3 greater than or equal to 0 is called non-negativity, because if you want to make something, it has to be nothing that is 0 or positive quantity cannot be negative. That's why we call them non-negative constraints. So when you are people viewing this lecture, you might want to pause and take a look at it. And also, whenever I solve a problem, what you could do is you can have the lecture, you can pause, and simultaneously you can create your own spreadsheet, and so that way you can walk in line with me. So you can play and pause, just see what step I did, go recreate that step by yourself, and then once you are done with that problem, go back and do it all by yourself, without the aid of my lecture. Then if you get the same results as you got, or if you could do the problem completely, so that means you have learned how to solve a problem using a spreadsheet. If you recall, in my syllabus that I sent to you, I did mention that there are some Excel functions that you should be aware of, and towards that I did put an Excel tutorial on the blackboard, so you can use that Excel tutorial, go back and practice some of those. So this week is for you to go and get familiarized with the Excel. So we will be using these functions: min, minimize, maximize, min, max, and logical statements, and a few other functions that you will be exposed to whenever we get to those problems that need to use those functions. This is a very typical problem, a very simple problem that people get exposed to in their introduction accounting classes and all. Okay, what it is it's a situation where you produce dry beans. Your sunk cost, that is a fixed cost, is $50,000 if you choose to produce, and then your variable cost is $650 per acre. Your revenue per acre is $700 per. That is $700. What is your long run break-even quantity, or BEQ? Of course, the formula is break-even quantity is produce enough to recover the sunk cost. Okay, at the same time you have to pay the variable cost. So the bottom that you see here, revenue minus variable cost, is a contribution margin per unit. So produce enough units such that the contribution margin is going to recover the fixed cost or sunk cost that has gone into the system. Any quantity on top of that is going to produce the profit. Any quantity below that leads to loss. So that's a break-even quantity. This is another situation in which there are different scenarios, and what I will do is, in my next lecture, I will take one of these two examples, create a simple spreadsheet, and perhaps maybe how to chart that, and then go back and change some dimensions and see how the graph reacts with respect to that. So that's some sort of a dynamic link that exists between the data and the graph. As I said, I will take one of these two, then start with. I will start with a simple one, then gradually build the complexity into the problem.